The universe is filled with ghostly particles that could help us better understand our existence. And yet, despite being predicted decades ago, we've never been able to detect them. They are the Relic Neutrino background. They're like the cosmic microwave background, only older, more elusive, and potentially much more abundant. These ghostly particles were born at the very beginning of time in the fiery furnace of the Big Bang and could hold important clues about what the universe was like in its first moments. But they're extremely hard to detect because, just like light, they move near the speed of light. It's difficult for scientists to tell where they're coming from, and they seem to be everywhere at once. It's as if you were trying to hear whispers in a hurricane. Neutrinos are tiny, nearly massless particles that rarely interact with anything. There are 3 types or flavors of neutrinos, and each of them has an anti-counterpart. The 3 anti-neutrino flavors are antineutrinos. Neutrinos can be created when other particles like protons and neutrons interact. We know they exist because we've seen their telltale fingerprints on events like supernova explosions and the behavior of certain particles in accelerators. But those are baby neutrinos. We also think there's a vast sea of older, more ancient neutrinos floating around us that date back to the earliest days of the universe. These relic neutrinos would have been produced when matter and energy were so hot and dense they were all moving at high speeds. Physicists think the conditions were so extreme back then that every few seconds the neutrinos would collide with something and change their flavor. But these changes were random, so some would turn into tau neutrinos, others into mu neutrinos, and still others into electron neutrinos. Since they were constantly changing flavors, it's impossible to know which one you'll get if you try to detect them today. And because they were born in a sea of other particles, they're hard to spot because they pass straight through ordinary matter as if it isn't there. Physicists believe this background of relic neutrinos is as old as the universe itself, dating back 13.8 billion years. That makes them even older than the cosmic microwave background, a faint glow of light that's left over from the Big Bang and that we can see all around us today. The relic neutrino background is a prediction of the standard model of particle physics. This model is like a periodic table for particles, except instead of chemical elements, it lists all the fundamental particles we know of and how they interact. One of the main pillars of the standard model is that the 4 forces of nature, the strong force, the weak force, electromagnetism, and gravity, are all linked together. The strong force binds together the center of atoms while the weak force plays a role in radioactive decay. Gravity is what makes things fall to the ground, and electromagnetism causes light waves to ripple across space. But for a long time, scientists didn't know how to unify the weak force and electromagnetism. In the late 1950s, physicists C.S. Wu and A. Salam figured out that both forces could be explained by particles swapping photons, which are the quantum of light, and another particle called a W boson. The problem was they couldn't figure out how to make the W boson fit into the standard model because it would have to be incredibly heavy. But then in the late 1960s, Sheldon Glashow showed that the W boson could be massless if the neutral current existed, meaning the weak force and electromagnetism could be carried by the same particle. This made the W boson fit into the standard model and paved the way for the unification of the 2 forces. He received the Nobel Prize in Physics in 1979 for this discovery, along with Abdus Salam and the late Steven Weinberg. When they were awarded the prize, Wu was already dead. The relic neutrino background is one of the predictions of this unified force. But to confirm it, we need to find a way to listen for neutrinos and tell where they're coming from. And there's one place in particular that scientists are hoping to catch a glimpse of these ghostly particles, the Borexino experiment deep underground in Italy. At this facility, scientists have built a sphere-like detector about 10 feet across and filled it with 280 gallons of liquid. It sounds simple, but the whole point of this setup is to block out all the noise. All kinds of radiation from space and the ground above can mess with the experiment, so the researchers built several feet of rock and concrete above the detector to block that radiation out. Inside the sphere, however, there's enough liquid to detect the tiny signals given off by relic neutrinos. Here's why. If a relic neutrino collides with an atom inside the liquid, it will knock an electron off the atom. When the electron returns to its starting position, it will release a pulse of light. By measuring the direction and energy of the light pulse, scientists can tell where the neutrino came from and how much energy it had. So far, though, the experiments haven't found any relic neutrinos, but they have found evidence of other rare neutrino interactions. Those discoveries are big news, too, because they help scientists learn more about the properties of neutrinos. They're also helping researchers test whether neutrinos have a property called mass ordering. In particle physics, mass ordering refers to the masses of neutrinos relative to one another. Currently, scientists know that the masses of neutrinos are different, but they don't know if the lightest type has the lowest mass, the second lowest mass, or the highest. In other words, they don't know if the mass ordering goes normal, inverted, or just maybe one of each. If the inverted order is correct, some of the relic neutrinos might have enough energy to trigger a specific reaction inside the Borexino detector. Researchers hope to collect enough data to find out if this is the case. But even if they don't find the inverted order, they will still learn something from the experiment. That's because every time they observe a neutrino interaction, they're actually seeing the interaction of an antineutrino. That's because most of the neutrinos in the sea of relic neutrinos would have changed into antineutrinos long ago due to a process called CP violation. CP stands for charge and parity refers to a type of symmetry. In short, CP violation means that a particle and its anti-counterpart do and act the same way under certain conditions. It turns out that the interaction between a neutrino and an atom is slightly different from the interaction between an antineutrino and an atom. So, whenever scientists see a neutrino interacting with something, they actually see an antineutrino interacting with it instead. If they find that the amount of CP violation matches what physicists expect, it will lend credence to the standard model. But if they find that it doesn't match up, it would mean that there's something wrong with the model. That could hint that there are new particles or forces of nature that scientists don't know about yet. So whether or not the Borexino experiment finds relic neutrinos, scientists will gain valuable knowledge about the fundamental nature of our universe. But here's the thing, even if we do detect relic neutrinos, they may outnumber all the photons in the universe by a factor of 10 to the 12th power, and that's a huge number. For some perspective, there are approximately 10 to the 80th power of photons in the entire universe. Photons are the particles of light. So, if we include all the electromagnetic radiation out there, including radio waves, X-rays, and everything in between, the total number of photons in the universe is likely close to 10 to the 130th power. If the relic neutrino background really does exist, then for every 10 to the 12th power photons out there, there's one neutrino. To put that in perspective, if you took all the water in the observable universe and spread it evenly over the surface of the Earth, each person would get a layer of water that's 136 feet tall. But that's not the only reason why detecting relic neutrinos is one of physics' ultimate challenges. It's also because they're so darn fast. These ghostly particles travel at around 99% the speed of light. At that speed, they complete a lap around the Earth in less than 1/10 of a second. Imagine you're trying to track down the source of a whisper in a hurricane. The relic neutrinos are the whispers, but since they're traveling at almost the speed of light, they're extremely hard to pinpoint. That's why the Borexino experiment has to be so precise with its measurements. The slightest uncertainty about the direction of a neutrino could throw off the entire experiment. But even if we can measure the direction of relic neutrinos, we still won't know which flavor they are. We won't know if they're tau neutrinos, mu neutrinos, electron neutrinos, or some combination of the three. And that's part of what makes this experiment so exciting. If it works, we'll learn that the standard model is right. But if we don't find what we're looking for, we'll be led to ask new questions about the nature of the universe. The answers to those questions could reveal new physics that could change our understanding of the cosmos forever. So even if these ghostly particles remain elusive, they're helping scientists search for answers to some of life's biggest questions. On occasion, we all need a little support. Our community helps us reach more people, create more content, and take our physics explainers to the next level. And you can help us keep our videos free for everyone forever. For as little as $3 a month, you can join our community and get fun perks like submitting a question to our inbox. We read and answer every email we receive. Your support really does help us make the best videos we can, so thank you for watching.